Hello everybody, we're going to be talking about continuity in this video. So a function that is continuous is a function that you can draw without picking up your pen or pencil. So based on that definition, we're going to look at the graph below. So is f of x continuous? So think about the definition that we just talked about. Can you draw the function without picking up your pen or pencil? So take a minute, pause the video, and decide for yourself. All right, so welcome back. So can you draw this without picking up your pen or pencil? So we're going to start at -5. So I'm going to draw on this with my pen. So we're drawing, and then it comes back up. But I can't do anything from here because there's a hole. I can't draw over that hole. So I'd have to pick up my pen and then keep going. So that tells us right there the function's not continuous. So make sure that if you have a hole, you know that the function is not continuous. So we're going to talk about different types of discontinuities. We have removable holes, that's what we just saw. So in a graph, if you have something where the function is just going in any sort of non-jumping, non-hole, so you're going to start, you have a hole, and then you keep going. So that's a removable hole. A jump is just what it sounds like. So we're going to start up here. You have a point and then a hole or something to that effect. That would be a jump. And an infinite discontinuity or an asymptote would be something like this. So we have an asymptote. I'll draw it in a different color marker. Say there's an asymptote right here. So our function would look like this. But you cannot draw this function without picking up your pen or pencil. So those are the different types of discontinuities that you're going to see. So in example 2, we have a function, so f of x equals 3x cubed minus x squared plus 2x minus 1. So we have to decide, is this function continuous? So we have to look at the different types of discontinuity and find out if we just saw any. So the question is, can I draw this without picking up my pen or pencil? And the answer is yes, I can. So that would mean that this function is continuous. All right, let's look at example number 3. So we have g of x equals 1 over x. All right, so can I draw this without picking up my pen or pencil? And the answer is no, because if I start to, obviously I have a big element in this graph, and that would be an asymptote. So this is not continuous. So, not continuous. And what type of discontinuity is this? Let's scroll back up and see what our options are. This is an infinite discontinuity because we have an asymptote. All right, so now you try these examples 4 and 5 and take a minute, pause the video, decide for yourself if it's continuous or if it's not continuous. All right, so we're back. Example number 4, so we have a piecewise function. We have to decide for ourselves if this is continuous or not. So if I draw this function, we have to ask ourselves, can I draw it without picking up my pen or pencil? So if I try to do that, I'm going to end up at this hole, and then the function drops down to this point and then keeps going back up. So is this continuous? No, this is not continuous. And what type of discontinuity is this? This is a jump. So from that hole, we jump down and then come back up. Or this is a removable discontinuity, sorry. All right, next example, example number 5. So we're looking at f of x equals tan of x. So where are the discontinuities? Let's see. We have a lot of asymptotes in this graph. So there's going to be a lot of discontinuities. So we have an asymptote, let's draw them in. So we have one at this point right here, and it's in between 2 pi, and of course these are negative, so that leaves us at negative 270 pi. All right, and then we move over, so let's draw our other asymptotes. We have one at, what is that point? That is negative 90. All right, and then we have another one. Because these points are getting close to the asymptotes, but they're not ever crossing them, and that is the definition of an asymptote. So we've got two more. We've got a jump, or an asymptote, where we can only get close to the point, but we can never cross it. We've got another one at 90, and then lastly, we have another one at 270 degrees. All right, what type of discontinuities are these? Well, we have asymptotes, so that means they're infinite. And lastly, on what intervals is f of x continuous? All right, so we have to look at what we just said to be our asymptotes, and we have to look at where they are continuous. So, based on our graph, anywhere in between negative pi over 2, which is 90, negative 90 degrees, and less than positive 90 degrees, or pi over 2, is going to be continuous. All right, if we scroll up, we say, where else is our graph continuous? So we also have pi over 2. So x is between pi over 2 and 3 pi over 2. All right, so now we have limits and rational functions. Let's look at the function. We have to decide how we're going to write this as a limit. So we have f of x, and it's approaching a certain point. So if we scroll down, x is approaching 2 of f of x, and we get 4. So how we write this with a limit is that the limit, and then we're going to say as x approaches 2, and how we write this is x, an arrow, and 2. So the limit is approaching our function, so we're going to write what our function is, x squared minus x plus 2. And when this limit approaches 2 of this function, we get our answer of 4. So 4 is our y value. So that's how we write our limit notation. All right, so another example, now we don't have an actual function with numbers or an actual example, but this is a more general notation. So we write the limit as x approaches a of f of x equals L. So in this case, we have our function, we don't know what it is, but it's f of x. X is approaching this point A, and we get our limit of L. Okay. So let's look at some examples. So now we have some different holes in our functions, and we want to write the limit as x approaches a of f of x. So what we have to say to ourselves is if we're going to get the same value coming from each side of the graph. So I'm going to start over here. So x is approaching this value a, and these are our x values. That's why it says x approaches a. So we're going to start over here, and we're going to follow the function. All right, so x is approaching a from the left-hand side. We should get the same value if it approaches from the right. So here we get this value L. If we come from the other side, we should get the same thing, and we do. So even though there's this removable hole, our limit is still L. However, we have a point here, so f of a, that's not going to be where our hole is. F of a is going to be the point at the function, so f of a is going to be 4. All right, so now we have another example of a hole. So we want to find the limit as x approaches a of f of x. So here, we start from one side and see if we follow the function. Okay, now we start from the other side. So we end up at the same hole, and that y value is L. So that means our limit is equal to L. F of a, however, now we don't have a point. We don't have a separate point. So f of a, we have a hole at this f of a right here. And because we have a hole, there's no actual point. So f of a does not exist. All right, so we have some more examples. We have a jump example, and we want to know what the limit is as x approaches 1. So as x is approaching 1 from the left-hand side, we come up to our y value of 2. As x approaches from the right-hand side, we get a y value of 3. Since these numbers aren't the same, we say the limit doesn't exist. If we wanted to find f of 1, what we would do is we'd go to our x equals 1 point on the graph, and we'd go up and see which value has the actual point in it. So if we went up and look at 2, 2 has a hole, but if we go up to y equals 3, then we see the actual point, so f of 1 equals 3. In our next example, so we want to find out the limit of f of x as x approaches 2. So we're going to start from the left and follow the graph. It goes down from the right. As we approach 2, we're not going to get the same value because the graph is going off towards negative infinity and then it's going up towards positive infinity. So the limit here does not exist. And the value of f of 2, so as we just said, one of the sides is going all the way up, one of the sides is going all the way down. So this does not exist. All right, so now we're going to talk about the limits of this function from different x values. So the limit as x approaches 3. So we're going to look at our graph, and you can see that it's coming from the same, it's reaching the same y value from either side. So that means that we have a limit, it does exist, and our limit is going to be 5. Now we need to look at the point f of 3. So at our x value of 3, we go up, and because the limit existed, we also see that that is a point with a y value of 5. All right, our limit as x approaches 0. So as x approaches 0 from either side, we get the same y value. So that means we have a limit, and it is 0. F of 0 is going to be the point at 0, at the x value of 0, and we get the point 0, 0. So f of 0 is 0. We have the limit as f of x approaches negative 2. So as the function approaches negative 2, we go all the way up and we see a jump or a hole, and then we come back down. So the y value at that point is going to be, well, it doesn't really matter because the function is not continuous, it's a hole. So our y value at negative 2 is going to be 4. That means our limit exists. Except our point at negative 2, we have a hole in the function. So we have to look at the point that we have, and our y value is just 1. So our function is not continuous here, but the limit does exist. Now at x equals 1, again, we see that our function is not continuous. I can't draw that line I can't draw the function without picking up my pencil. So this means that from different sides, you're going to get different y values. That means the limit does not exist here. However, f of 1 is a point that does exist. So we're not going to look at the hole, but we're going to look at the actual point, which has a y value of 2. Now we're going to look at the limit as x approaches negative 4. So as we approach negative 4, we can see that the function is the same coming from either side. You're going to approach the same value, which is 0. And then f of negative 4 is also going to be 0. Now we have the limit as x approaches 4. So we're at 4. 1, 2, 3, 4. All right, so from either side, you're going to get the same number. So we have the value of 4 for our x value. And if we take a look at the point at 4, at the x value of 4, we're going to see that we have the point 4, 4. Okay, if you said any of the above limits do not exist, explain why. So we said that the limit doesn't exist in question D. So explain why. Let's think about this. If we look at the graph as x approaches 1, so we have this whole big jump right here. It's not continuous because as we approach from one side, the value isn't the same as when we approach from the other side. So as we approach x equals 1 from the left, our y value is not the same or does not equal the y value that would be if we approached from the right. So therefore, our limit doesn't exist.